Hi everyone, my name is Asif. I'm a PhD student at the Chair for Compiler Construction at TU Dresden in Germany. Today I'm going to talk to you about our work on polyhedral compilation for Racetrack Memories. This is a joint work with my colleagues from TU Dresden, Hauke and Geronimo, and our collaborators from ETH Zurich, Tobias and Torsten. Before talking about the compilation, let's first talk about the technology itself. So racetrack memory, for short, let's call it RTM, is a promising new class of the emerging non-volatile memory technologies. So compared to other memory technologies where there is normally a single bit stored per cell, in RTM a single cell can store up to 100 bits. And the reason is in RTM a single cell is a magnetic nanowire. It can be horizontal or vertical, and each nanowire, which is also called a racetrack, can be split in multiple magnetic regions, small magnetic regions, which are known as domains. Domains are separated with domain walls, and each domain can have one of two magnetization directions, right? So each magnetization direction represents a bit, a 0 or a 1. Okay, so for accessing data from the cells in RTM, there are normally one or more access ports associated with each cell. To motivate, why do we talk about RTM in the first place? So this table kind of gives a direct comparison of RTM with all other kind of established memory technologies. If you look at the characteristics, so the RTM, so the cell size is less than or equal to 2, far less compared to other memory technologies. Endurance is not an issue. The read time is theoretically compared to that of SRAM. The writing, which is normally an issue in non-volatile memory technologies, both from the latency and energy perspective, is not an issue in here because the physicists developed RTM believe that we can theoretically use a different switching mechanism which consumes less energy and takes much less compared to other non-volatile memory technologies, much less time. Leakage is not an issue because it's non-volatile. So this basically motivates the exploration of RTM from different angles, and we are doing exactly that basically in this research. To talk about the overall architecture, so it's mostly similar to other memory technologies. So we have different abstractions. So we have banks. Banks are subdivided into mates and subarrays. And each subarray is then an array basically of DBCs. A DBC is a set of nanowires, a group of nanowires, which are connected in a way that the access ports in all nanowires, they point to the same location. The data is stored in a bit interleaved fashion. That means if I have a variable or a memory object v0, so I can store b0 in the first racetrack, b1 in the second racetrack, and bt-1 in the t-1 racetrack. The access ports can then be moved in a lockstep fashion, so all of them can be moved to the next step, and so on. And this basically also enables accessing all t bits of a memory object in parallel, right? Let's briefly talk about the motivation. Why do we need specific compilers for RTM? The reason is RTMs are inherently sequential in nature, which means if we want to access this bit here in a racetrack cell, we have to move it all the way to the access port position. And this shifting process, I've marked it red intentionally because it's expensive. It takes almost same energy and time as is required for a read operation. Theoretically, I said in the beginning, RTMs are comparable to SRAM, but in the worst case, if we bring shifts to the picture, so the worst case latency can be as high as 26 times that of SRAM. And in addition, it also brings other challenges like location dependent or variable access latencies, position errors, and so on. Okay, so how are shifts basically incurred in array accesses? So let's take the typical matrix multiplication kernel, and let's focus on one particular array B. So the assumption is that array B is stored in racetrack memory in a way that each row is stored in a separate DBC. So we talk about row 0 here. So if we take k equal to 0, so this is our iteration space. So when I is equal to 0, j equal to 0, we will access b0, 0, so which is basically this first position here. But when we increment j, so then we access b0, 1, which means we have to move the access port by one position, and we continue this until the iteration of the j loop is complete. But when we increment I, so then we need to access the same row again, which result in a very long shift from b03 to b00. And these long shifts are not only problematic in the sense that they stall execution, but they also incur energy, which increases the overall energy consumption. So now we wanted to ask ourselves if we can get rid of these long shifts. So we searched for answers, and we already found that there are a couple of works available for instance, in the first reference here. So the author in here basically proposed manual transformations and demonstrated that if we do these transformations, so if we access an array in a zigzag fashion, we get rid of the longer shifts in array accesses. In the second reference, so these guys proposed a similar idea for instruction strings. So in instruction memory, if you have a basic block, which is basically a repeating basic block like a loop or something, so then you have the exact same problem. At the end, you will have to have a longer shift to go to the first instruction. So these guys split the basic block and map it to RTM in an intelligent way to completely get rid of the longer shifts. And now the important question is, can we somehow do these transformations automatically? So this is basically the inspiration for this work, or the motivation for this work. Can we make compilers to do these things automatically? So the answer to this again is yes. So we tried to explore this thing. We at the end were able to generate code which looks like this. So with this code, the idea, the constraint is that while doing these transformations, one should never disturb the program semantics. So they should be preserved at any cost. So with this transformed code, if we access the array B again, so I'm taking the same iteration space in the same array row. So I access all elements for I equal to 0, and now for I equal to 1. So I'm not accessing array B in the forward direction, rather I'm accessing it in the backward direction, which means that the access port in here will now start moving from here. So we came this in a forward way, and now we're moving backward, and for the next iteration I will move forward again, and so on. So this way we get rid of the longer shifts in RTM. Okay, so to do this, we were looking for a model which basically allows reasoning about individual statement instances and individual memory accesses, because in here we talk about them. And the polyhedral model does exactly that. So it allows reasoning about individual memory accesses and statement instances. So I expect in here that people are aware of the polyhedral models. I will not go to a lot of details, but I'll briefly introduce the main components. So it operates on scopes. For an application, for a kernel, or for a loop nest to be qualified as a scope, it has to satisfy a set of constraints. I'm not going to the details in here. It consists of three main components: iteration domain, which is nothing but a set of statement instances; schedule basically defines order on this set of statement instances; and memory access relation basically maps program statement instances to the memory accesses. Let's take an example to clarify this further, because these are important concepts. So for iteration domain, if I take k equal to 0, because in here I cannot go to the third dimension, so let's restrict this to 0. And then for I and j for this kernel, so this is the whole set of statement instances. Now for the iteration domain, give me the whole set of statement instances, but it does not define order on the statement instances, the execution order I mean. So one never know if this statement instance will execute before this one or after this one, or how will this be executed. So the schedule provides exactly that information. So it defines order on the statement instances. In other words, it basically assigns a logical date or timestamp to each statement instance, and then this is followed lexicographically. So for instance, in this case, this already tells me that these statement instances will be executed in this order. And access relation maps, as I said in the beginning, statement instances to the array accesses. For this work, we use the polyhedral optimizer in LLVM, the LLVM compiler, which is Poly. So Poly uses schedule trees to represent schedule. And for schedule trees, so this is the typical the example of the schedule tree for our running example. So it has basically different nodes. So the domain node, which is typically the first node in the schedule tree, represents the scope domain, and then the band node basically represent a partial schedule. So in this case, it expands the dimension I, the statement dimension I, and similarly the second band node expands K, and so on. Similarly, there's a leaf node for each statement. Sequence node, basically if you have more than one statement instance, if you have more than one statement in a scope, and sequence node basically defines the order in the statements. So let's, with all that in mind, let's start with the transformations. So first, the schedule transformation. So we only do the transformation if we know that there are repeated accesses to the memory location. So if there are no repeated accesses to a memory location, there is no need for transformation, because we know there will not be longer shifts, right? So this is the thing that I clarified in the middle. So if elements in a DBC are accessed more than once, only then it's possible that you will have longer shifts. So this is the first check. So for instance, in this example here, each location of C is accessed only once. So we don't need to do any transformation for C. But if you have something like this, so we already saw that arrays in this kernel are accessed more than once, which means we will have longer shifts. So our analysis pass will tell us, okay, this is something which has the potential to be optimized. So then our optimizer look for basically two things. One is what we call an alternation candidate. So let's quickly go to the transformed code. Okay, so in here we basically have loop J, which is what is alternated. So we call this loop as an alternation candidate because this is the one which is split. And another thing is this alternation decision is taken based on another loop, which is loop I. So we have alternation candidate, and then we have alternation base, right? So for alternation candidate, which in this case is loop J, we look, so we do this analysis for each individual array, for each and every array. So for instance, for array B, we look at the innermost index of B, and we found that, okay, so J in this case is the alternation candidate, right? So this is intuitive because the innermost dimension basically is something which unrolls inside a DBC, right? So whenever there is a change in J, you will have a movement inside a DBC. So that's why it's our alternation candidate. For our alternation base, so in this case, which is I, so we select our alternation based on the analysis. So for instance, in this case, when we took k equal to 0, we already found that a new iteration of I cause repetition to the accesses to the location in B. So that's how we decide our alternation base. So in this case, now we have our alternation base is I. So now that you have AC and AB, the optimizer goes on and do the transformation. So what we do is we take the schedule tree, start traversing it bottom up. So we start from the leaf node and try to locate our ACs and AB in the schedule tree, right? So the first step it does is it first locates AC in the schedule tree. So in this case, it goes to the first band node, it compares the dimension of the band node with basically the AC, which is also a statement dimension. So in this case, J is equal to our AC, so we mark it as an AC. Then we locate our AB, so we start from AC upwards and look for AB. So the AB in our case was I, so if you compare I with the dimension of this band node, which is K, this will say, okay, this is not AB. Then you go up and you find AB here. you are all set to do the transformation, but we only transform a C if a set of constraint is satisfied. The first and probably the most important one is that a C should not carry any dependencies at all. We make sure that we do not violate any dependencies. And the second condition is that a B should be above a C in the schedule tree. And this again makes sense because otherwise you cannot make the alternation decision based on a B if it is below it. And once you do that, you are, so in this case we pass all tests, so we are ready to go. So we split the schedule in two smaller schedules, into partial schedules. The first one basically is the one which moves in the forward direction, and the second one goes in the reverse direction, the -j. Okay, so with this we will see in a bit that it works perfectly fine for a set of kernels, but for other it doesn't. So for instance, in some cases the scope statement so they carry dependencies, so the dependencies strictly prohibit loop transformation at all. So this is one example. So in here aij, so each iteration of the statement is dependent on other iterations, so you cannot do any transformation in here. So in this case we use layout transformation basically to eliminate or mitigate the longer shifts, and this is particularly works very well for stencil kernels. So let's see how we do that. We find the number of distinct rows that are touched or accessed by each iteration of I. So for instance, in this case, this will be 3, and it's obvious in here. So for each iteration of I, you access row I minus 1, and row I plus 1 means 3 rows. So with that in mind, we go and transform the original layout by storing all 3 rows in one column in the transformed layout, right? So if we do this, we completely eliminate shifts in loop J. So if you look at the matrix A here, so assume it's bigger and cannot fit in RTM, so we can employ blocking or tiling, the classical tiling techniques to take a block which fits in RTM. So for instance, this is our original layout. So we have dr rows, we identified them, and in the transformed layout, we stored them, all 3 rows in one column, right? So what happens is now, for the entire iteration of loop J, you do not need any movement, right? So if each row is represented, so let's say each row is stored in 1 DBC, you do not need any movement because the assumption is that in the beginning, the access port points to location 0, right? So you will always access elements from the first column in all DBCs, so you don't need any movement, right? So when I is 1, you don't need any movement because this is your access space. If I is 2, that means the next iteration of loop I, so you move the first 3 DBCs by 1 position, and all other DBCs are still used, so you access these elements which are represented with this, are highlighted, are kind of shown with this red line. For I3, you access these elements, so you incur only shifts in these 3 DBCs and only 1 shift. And for I4, you access these elements, and this is continued. So you will never come back. That's the good thing, right? So you access all these elements until you do not need them anymore, and then you move to the next position. The side effect is that this may affect the DBC's utilization. So assume that you have very long rows. So if you store 3 consecutive rows in the first column, you need a lot of DBCs, and it's possible that some of the position in those DBCs are empty, right? So this may affect utilization of DBCs. This is something which we did not evaluate, yeah. So with that, let's see how the results look like. So for the experimental setup, we took 2 benchmark suites, Polybench and so these are some kernels from the Switzerland atmospheric. So they have a atmospheric model in Switzerland, and we took 3 representative kernels from them. This is called Cosmos. So 3 kernels and Polybench, the entire set of Polybench benchmarks for evaluation of Racetrack Memories. So we used RTSim, the Racetrack Memory Simulator, and we evaluated a number of configurations. So identity, we didn't change anything. We evaluated the original program for shifts and latency and energy consumption. ISL is the default polyhedral optimizer scheduler in Poly. So we evaluated this because we wanted to see how this performs from the RTM perspective, right? So we will see in a bit that it's kind of arbitrary. RTM-ST is our schedule transformation. TM-SLT is our schedule plus layout transformation. RTM-ST ISL is basically ISL when our transformation are applied on top of the ISL transformations, and this is our transformation on top of ISL, but this includes the layout transformation. Let's build the results step by step. So on the x-axis, I show all the benchmarks. So these are the 3 Cosmo kernels. This is the whole set of polybench kernels. On the y-axis, I show the RTM shifts, which are normalized to the baseline identity configuration, right? So for the schedule transformation, on average, on geometric mean, we reduce the number of shifts by 9%. But as you can see, in most of the kernels, the number of shifts are not reduced. The important point probably to highlight here is that it also does not increase the number of shifts, right? So, and this is obvious because we always analyze a scope. If we see any potential for optimization, we apply transformation. Otherwise, we just forward it to the next step. So we don't do anything. So we do not expect it to increase the number of shifts, and that's exactly what happens. If I include the layout transformation in my results, so the shift reduction basically increases to 22% on average across all benchmarks. For ISL, so it on average reduces the number of shifts from 6 to 7%, but the important thing is that it can also increase the number of shifts by more than 2 times. So this is something which is arbitrary, right? So we cannot trust ISL, and this is anyways not expected because it's not considering RTM. This is the overall set of results for all configurations. So on average, the shift reduction is by 31%. So this is again the shift result, but only in those benchmarks where our transformation always affects shifts, and the shift reduction is by 53.3%. So this means our transformation either does not improve shifts, but also does not exacerbate shift. But when it does, it can reduce the number of shifts by an average of 53%, which already is a very promising number. So these are all benchmarks where ISL plus our transformation affects the number of shifts. So this only excludes those benchmarks where nothing changes the results. The overall reduction is around 40%. For the latency, we also included an ideal RTM configuration, which is nothing but a random access RTM. So in here, we assume that RTM does not have any shifts, so it has 0 shifts, right? So just to get a lower bound on what we can achieve if we do even further optimizations. But on average, so the ISL RTM SLT, this points to the wrong bar. So this yellow one here reduces the number of the latency by around 18%. The important point, again, another important point in here is that the latency improvement, so it's not proportional to the shift reduction, right? So in some kernels, we observed more shift reduction but less improvement in the latency, and the reason was that the kernel itself basically had very little shifts. For energy consumption, so the overall energy consumption is around 40%, but it generally follows a similar trend to the latency reduction. Okay, so let's conclude the presentation. So the RTM is promising from the latency, capacity, and energy perspective, but shifts are problematic, and shifts in arrays are particularly problematic because you have these longer shifts compared to the shifts in scalar accesses. And on the positive side, the longer shifts, so the shifts in arrays in general are kind of predictable, right? So you can optimize them relatively easily compared to the shifts in scalar accesses. So we propose pattern-based transformations which effectively mitigate shifts in majority of the kernels, but the important note, it preserves the other optimization by the ISL, by the default polyhedral optimizer. In future, we basically are working on exploring the classical transformation in much more detail, and right now we are doing the optimization on a loop nest by loop nest basis. So we treat each individual loop nest separately, and in future we want to explore across loop nest optimization as well. So that's all for now, but if you have any question, please come to the live session on the 21st of September and ask those questions. I'll be happy to answer them. But thank you for now. Bye-bye.